for you. What is a nanometer?
A unit of measurement.
Right, it's a unit of measurement. Do you know how small a nanometer is?
Really small.
It's really small, right? So let's see how small a nanometer is. I have this meter stick right here. If we were looking at this tree, that tree would be about this tall from the height of the table, right? If we were to compare this tree to a leaf, it would be about 1/10 of the meter stick. So that's about right here. It'd be this big, right? That's how big the leaf would be. If we were to compare a thumbtack to a leaf, it would be about 2/10 of the leaf. So that's about right here, a thumbtack. If we were to compare a strand of hair to a thumbtack, it would be about 2/100 of the thumbtack. So really, really small. But if we were to compare a nanometer to a strand of hair, a nanometer, there would be 90,000 nanometers in one strand of hair. That's how small a nanometer is. Today, we will be dealing with substances that are so small that you're going to be a nanoscientist. That brings us to the question of the day, which is, how is energy transformation similar in solar cells and in plants using photosynthesis?
Where have you guys seen solar panels?
Electronics.
On electronics, okay, such as like calculators. Good observation. What do solar panels actually do?
They use energy from the sun.
Right, they're actually sheets of solar cells that actually take in solar energy and then convert it into electricity to be used. Today, as nanoscientists, you're going to be working with these and making your own solar panel. But before we begin, we do need to discuss our safety rules. Just like any scientist in a lab, you need to be wearing your gloves at all times. We're going to keep them on for the whole explore. You're also going to need to be wearing a mask. We're going to be working with some powder that you don't need to breathe in. And of course, we're going to be wearing our goggles to keep our eyes safe. Now I'm going to be passing out the job cards. Once you get your job card, I need the materials manager to come up and get the supplies at the front of the room. Now that you all have your materials, I need you guys to get out the mortar and pestle. It looks like this. And I also need you to get out the little container that has the white powder in it. It's called titanium dioxide. And I need you to put those in the center of your table. And then I need eyes up front. In the center of your table, you have a white powder. It's called titanium dioxide, also known as TiO2. It's found in your toothpaste, white paint, and even sunscreen. Now, just like these substances, we don't eat them. Yes, we brush our teeth with them, but we don't actually ingest any of the material. So this is why we're going to be wearing our masks while we're using this powder. Okay, so I need my principal's investigator to take the mortar and the pestle and put it in front of you. And then I need you to take the titanium dioxide, or the TiO2, and put in a very tiny bit into your mortar and pestle. And then once it's in there, I want you to grind it up, grinding motion. Not smashing it, you're grinding it very slowly. Okay? So now I want all of you to do exactly what I did. I want you to take your titanium dioxide. I want you to put a little bit in your mortar, and then the principal investigator is going to be crushing it in the mortar. Next, we're going to be adding acetic acid solution. What do you think acetic acid is?
Something acidic.
Something acidic? So very good. It's actually vinegar. In what other experiment have we also used vinegar?
The milk one.
Right, the one where we curdled our milk. Very good. Okay, so now I need my principal investigator, who has the mortar with the crushed up titanium dioxide, to continue crushing it adds a pipette full of our acetic acid or vinegar. It's very important that you do it slowly, and we don't want to create any bubbles in our mixture. Now that the principal investigator has crushed up our mixture of our acetic acid or vinegar and titanium dioxide, we're going to take turns crushing it. So going clockwise, starting with the principal investigator, we're going to take turns for a minute, and we're going to use the same crunching motion that the principal investigator used at the beginning. So we're going to set the timer, and I want you guys to take turns clockwise for a minute. A minute's up. Now I need you to make sure the mortar is in the principal investigator's hands. And now I want the recorder to pour in our soapy solution. This is also important that you pour it in slowly. Again, we don't want any bubbles in our mixture or our solar panels won't work. Now we need our mixtures to sit for 5 to 10 minutes. So now I need the materials manager to bring up your mortar with your paste in it up to the front, and we're going to leave them up here. We're going to continue our discussion. Today we're going to be using multimeters. What is a multimeter?
Something that measures voltage.
Right, so multimeter measures voltage, current, and resistance. Today we're going to be using it to measure resistance of our glass plates. So these are the glass plates we're going to use. Why do you think we're measuring resistance of our glass plates?
To make better solar cells.
Right, because we want our solar cells to work. So the resistance on the glass plate actually has to do with the motion of electrons across the surface. So when using the multimeter to test for this resistance, it's super important that you only use the ends to touch your glass plate. Don't touch your partner with it. That's very dangerous. It's also important to make sure you have it on the correct setting. Look at the one up here on our PowerPoint. These are the settings they should be at. When looking at the numbers for a multimeter, we're actually looking for a really high number because it means a high flow of electrons are being moved across our surface. If the number's too high, you'll see the number 1, and that means there's an overload. If the number's too low, you won't get a reading, and that means our solar panels won't work very well. So go ahead and measure the surface of your glass with the multimeter. Our 5 minutes is up. I need our materials managers to come up and get your mortar with your paste. I also need you to come up and get your glass plate and a craft stick. Now that you have your materials at your place, I need the recorder to get the glass plate and the craft stick and get a tiny bit on the edge of the craft stick out of your mortar, and then paste it on the top part of your glass. And that's all you need to do with it. Eyes up front as soon as you've done that. Recorders, again, you're getting like a tiny bit of paste on the edge of your craft stick, and you're putting it on the top part of your piece of glass. Now that you all have a little bit of paste on the top of your glass, I need the recorder to take the craft stick and gently back and forth spread the paste all evenly over the glass surface. It's important that it's even so our solar panel works all the way around. Okay, now that everybody's glass plates are evenly spread with the paste, we're going to be taking them up and taking them back to UT to bake them, and so we can bring them back and do more with them next time. I need the materials managers to bring back the glass plate, the mortar, and the craft stick.
Today we used a multimeter. What does a multimeter test for?
Voltage.
Voltage. What else does it test for?
Current.
Current. And one more thing.
Resistance.
Resistance, right. So do you think glass, based on our testing today, is a good conductor?
Yes.
What evidence do you have to support that?
Our multimeter results.
Okay, so it showed on one side of the glass that low resistance? This is because we have something over the glass that makes it a good conductor. Glass is not usually used as a conductor, it's used more as an insulator. So do good conductors have low or high resistance?
High.
Good conductors have high resistance? Actually, guys, they have low resistance because resistance is the resistance of electrons flowing through the object. So if you're a good conductor, you will have high amounts of electrons flowing through, meaning that it has a low resistance. So today we were nanoscientists, right? And we figured out that nanoscientists measure things that are very, very small. So way smaller than this little piece of hair you can't even see from where you're sitting. And reverting back to our question of the day, how are solar cells, like what you made today, and photosynthesis related?
They use the sun for energy.
They use the sun. Do they transform the energy from the sun?
Yes.
Good. So, in photosynthesis, where do we find photosynthesis happening?
Outside in the plants.
In plants. Do plants need sun for photosynthesis?
Yes.
Yes. Does it need to be hot for photosynthesis to occur?
No.
No, right. So even in Antarctica, if the sun is shining, plants can do photosynthesis. In plants, there's a molecule called chlorophyll, and this is what it looks like. And this is another molecule called anthocyanin. What are similarities between these two molecules?
The shape.
The shape. What kind of shapes do you see in them?
Rings.
Rings. So I want to see thumbs up or thumbs down if you think that these two molecules will be similar in making photosynthesis happen. So chlorophyll definitely makes photosynthesis happen. Do you think anthocyanin will also make this happen just because they're similar in structure? Thumbs up or thumbs down? All right, we see some conflicting hypotheses. We're going to figure this out next time when we come back and we work on our solar cells again.
Who's heard of a renewable resource?
Me.
Awesome. Can you tell me what it is?
Something you can use over and over again.
Right, something I don't have to just use once and throw away. I can actually use it several times. Can you give me an example?
Water.
Water. What about our solar panels? What kind of renewable energy do they use?
Sunlight.
Sunlight. Very good. So sunlight's actually something you can use over and over and over again because we have a never-ending supply. So these are some really cool inventions done with solar panels. We mentioned the calculator previously in this lesson, but also these speed limit signs that have the flashing yellow, that's actually powered by a solar panel on the top. This one's actually really cool. It's a bag that you can charge with solar energy, and what you can do is plug your phone charger in the middle of the day, and it charges your phone while you're sitting outside. Solar panels are used in everyday objects, and your job is now to invent your own. We're going to pass out a worksheet, and your group is going to come up with their own invention. Now that you guys have had time to invent your own cool inventions, would anybody like to share theirs?
Me.
Okay.
What about a cooler that has a solar panel on top so it cools your drinks? Instead of the sun making them hot, it actually helps keep them cool.
That's awesome. That's a great invention. Does anybody want to share anything else?
A solar laptop.
A solar
So you can do
laptop.
homework outside.
Homework outside. Very smart. Very good inventions, guys. Now we're going to start the show off what you know.